This is where we must necessarily draw a line between the actual AC source and our imagined DC equivalent capable of supplying the same amount of average power. As we've demonstrated, average power is peak power divided by 2. Several methods exist for determining peak power. Notably, peak power equals voltage peak times current peak, voltage peak squared divided by resistance, and current peak squared times resistance. Either formula should yield the correct peak power value, and dividing peak power by 2 results in our average power. Thus far, you should be tracking. The leap of faith occurs when we say that there's an effective or RMS voltage and/or current value that would yield the same result. The same quantity of average power can also be experienced given voltage RMS times current RMS, or voltage RMS squared divided by resistance, or current RMS squared times resistance. This first equivalency is of little use to us, since it makes use of 2 unknowns. The second and third iterations, however, allow us to establish some equivalency between peak and effective values. Let's solve for effective voltage first. Given average power equals voltage peak squared divided by resistance divided by 2, one can also say it equals effective voltage squared divided by resistance. Simplifying the expression on the left-hand side, multiplying both sides by R removes the resistance from consideration. We can now square root both sides. You can probably see where this is going already. Square rooting both sides yields an effective voltage value equals the voltage of peak divided by square root 2. Note the square root of 1 is 1. In summary, our imagined equivalent effective voltage equals our peak voltage divided by square root 2. This algebraic manipulation isn't just a party trick, but rather proof that demonstrates specific voltage, current, resistor, and power values aren't necessary when calculating effective voltage values, but rather this result can also be achieved using solely general concepts and algebraic manipulations. Where does 1 over square root 2 come from? Right here. Because average power is half of peak power, 1 over square root 2 is the square root of a half. Get it? 0.707 of 0.707 is 0.5. We could also demonstrate the origins of 1 over square root 2 when solving for effective current values using a similar procedure. Using our third average power formula, being equal to current peak squared divided by resistance divided by 2, one can also say it equals current RMS squared times resistance. Removing the resistance term from consideration by dividing both sides by R, and then taking the square root of both sides, ultimately yields current RMS value is equal to the current peak value divided by square root 2. In summary, our imagined equivalent effective current equals peak current divided by square root 2. As previously, specific voltage, current, resistor, and power values aren't necessary when calculating effective current values, but rather this result can also be achieved using solely general concepts and algebraic manipulations. Again, where does 1 over square root 2 come from? Right here. Because average power is half of peak power, we pick up the 1 over square root 2 term along the way when we solve for an imagined equivalent effective value that would deliver the same steady state average power figure. Alright, that's enough mathemagic for today. Like I said, you don't need to dwell on these details since this isn't a math class, but this should quell any doubts about the origins of 1 over square root 2 if you previously had any curiosity. What I do care about is your ability to use these results. The effective or RMS value of a sinusoidal waveform is 0.707 of its peak value, and the peak value is roughly 1.414 times the effective or RMS value. Do not mess this relationship up. Importantly, since effective values convey far more usable information than peak values, it should be noted that unless otherwise explicitly stated, all AC voltage and current measurements are to be assumed in terms of effective or RMS values. This means if you grab an AC voltmeter that says 120 volts, you can rest assured it's saying 120 volts RMS and not 120 volts peak. Given an effective value of 120 volts, it can be easily demonstrated this correlates to a peak value of 169.7 volts. Like I said, don't mess this simple relationship up. Peak is greater than the effective value is less than peak. Unless explicitly directed otherwise, you can assume all AC measurements are expressed in terms of effective or RMS values. In conclusion, this lecture unveiled the mathemagic origins of 1 over square root 2. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.